Hello. In this lecture, we're going to continue our work on understanding failure criteria in ductile materials. Um, we discussed two different criteria in the previous lecture. The first one is called the maximum principal stress theory, and the second one was called the maximum shear stress theory. And we will build on that. So if you just then recap the maximum shear stress theory, MSS, we discussed three different cases. Case one, sigma A is greater than sigma B is greater than 0. And the line representing this is sigma A is greater than the yield strength of the material, which is here. And then case two, where the zero stress lies in between the two given principal stresses, and that turned out to be the equation of a straight line, and this equation of the straight line is right here. And then case three, when the two principal stresses are both negative in compression, so it turns out to be sigma B is less than or equal to minus sigma yield as the yield criterion. So in all of these cases, what happens is that we would have a particular design problem in which we have a load line, and the load line means that the stress state is defined by a point and on that load line. For example, point A could be a combination of sigma A and sigma B right here, and we can consider increasing both of them proportional to each other and find out what is the maximum value of the sigma A and sigma B that is possible before failure. So that's kind of what we will do in considering applications or examples in the future. Now what I would like to do is discuss a third theory, and that is based on this concept. Every material has a stress state, and the stresses can be divided into two parts. One part represents hydrostatic compression or tension, so the stresses are equal in the three different directions. And then on top of this, we would have deviations from this very highly symmetric system. And the deviations from this highly symmetric system are assumed to cause failure. So what we would like to do is compute the energy stored in the hydrostatic component of the stress, and then compute the energy stored in the deviations from that, and find a condition such that when the deviations in the energy stored exceed a critical value, then we would assume that the material has failed. So this is the idea behind the next topic, which is what we call the distortion energy theory. And that's what I'm going to discuss right here. So in the distortion energy theory, which is also called the same, is known as the octahedral shear stress theory, and it's also known as just the shear energy theory, or the von Mises criterion, or the von Mises-Henke criterion. All of these terminologies are equivalent to one another, and therefore we will consider only one of them, which is the distortion energy criterion or theory. So in this theory, the stress state, if we are given the three principal stresses, or we have succeeded in changing the stress tensor into the three principal stresses, then we can write on the cube, on this particular cube is a point in the medium. Like if you have a point in the medium, I want to just say a couple of words on this. Every point in the material is not characterized by a stress state at that point. However, we always have to think that around the point there is a cube, a very small cube, and on the faces of that cube we would get forces per unit area. These forces per unit area, we're going to call them stresses. And in the case that we succeed in rotation of the stress tensor, we would not have shear stresses on these faces, and we would have only three principal stresses, and that's the situation right here. So if you have three principal stresses, sigma 1, sigma 2, sigma 3, you can break up the three principal stresses into an average value plus the difference between 2 and the average, 1 and the average, and 3 on the average, such that when you add this component to this component, you get back the sigma 2 and so forth. So the average value is basically going to be the average of the three principal stresses. And the average value, we can compute it, sigma average, AV, will be equal to sigma 1 plus sigma 2 plus sigma 3 divided by 3. So the stress state is broken into a hydrostatic component, and this is called hydrostatic component, and another component called deviatoric component. That's the terminology that is used. So this is hydrostatic and this is deviatoric. This one is the dangerous one. So this is causes failure. So this is causes failure. And we need to figure out what is the energy stored in this deviatoric component that can cause failure. So this is our job right now, is to consider this situation. So to determine that, what I'm going to do is write down the equations for the elastic energy. So the elastic energy, total elastic energy per unit volume, that's very important, is we know that is 1/2 times the stress times the stress times the strain. But we know that there's three components, so it will be strain 1, stress 1, plus strain 2, stress 2, plus strain 3, stress 3. And that's when we have just principles, right? If we have other than principles, then it will be a longer expression. Now, what we wanted to do is go a couple of steps. First, we're going to eliminate all the strains and write them in terms of stresses, and then substitute there and find the total energy in that cube of material, assuming that cube has a unit volume. Remember, unit volume. So we know that the stress, for example, is related to the strain in this fashion. Epsilon 1 by Hooke's law is 1 over E times sigma 1 minus the Poisson contraction. That is, if we have other components of stresses on the material. Each one will give you a Poisson contraction, and so forth. So we can write epsilon 2 and epsilon 3, and then put back this into the total energy per unit volume, and that will give us the final result is without going, just basically substitution with algebra. We find that U total per unit volume is 1 over 2 times E. E is the elastic modulus, times sigma 1 squared plus sigma 2 squared plus sigma 3 squared, because when you substitute for epsilon 1, then you get all of these stresses, and then you get squares, right? But then you have also cross terms, and these cross terms can be rearranged to be 2 nu times sigma 1, sigma 2, and then you permutate. So sigma 2, sigma 3, and then sigma 3, sigma 1. Permutations. So that's kind of the total energy stored in that cube. Now, I'm going to say I have a couple of steps. Number one, I want to find out what is the energy stored in the deviatoric part. Like, I don't care about the energy stored in the hydrostatic component because that's so symmetric the material doesn't fail. So I want to subtract that out and find the deviatoric part. And in order for me to do that, I can apply the same formula that I derived right now to the case when sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to a number, and that number we're going to call it sigma average. That's the case that we'll consider. So for the special case when we have the case, let me just start a new page here. So in this case, when I have sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to an average value that we found, then the energy per unit volume that we derived, the same formula that we derived here, which is this formula. Then I take sigma 1 and I put sigma av. Take sigma 2, I put sigma av, and so on. Everything is the same. And U total becomes now U sub V. U sub V is volumetric energy. We're going to call it volumetric energy. That is the energy stored in volumetric distortions due to this average stress, which doesn't cause any harm. So U volumetric is going to turn out to be 3 times sigma average square over 2E. All of this multiplied by 1 minus 2 nu. Now, I'm not interested in that. I'm interested in U distortion, the distortion energy, which is the difference between the total that I found minus the volumetric. So if I go back, I have now to consider two equations, right? One for the volumetric, which is right here, and the other one is going to be for the total, which is right here. So if I consider for the total, then I will have another equation here, and this equation will be, in this equation you have sigma 1, sigma 2, sigma 3, but in the volumetric equation you have only sigma av, but note that sigma average is just 1/3 of sigma 1 plus sigma 2 plus sigma 3. So in this case, you get a situation that everything, when you do the subtraction, you will get the result that looks like this. U distortion is equal to 1 plus nu over 3e, and then this is multiplied by 1/2 of now the differences between 1 and 2 square, and 2 and 3 square, and then 3 and 1 squared. And that is the energy stored in distortion. So that will be sufficient for us to, if we know what is the critical value. So the next step now to determine failure is that we want to find the critical value of this energy at which failure occurs. And to find that critical value, we have only information from tensile testing, which is uniaxial. So in the uniaxial case, I can still find the distortion energy because I have a special stress state. And the special stress state is sigma 1, and then 2 and 3 are both zeros. And not only that, but at yield, sigma 1 is S yield. So the critical condition for that to happen, for the distortion energy, critical value, the distortion energy, which is what we want, critical value. value is for uniaxial. And the uniaxial critical value is we have sigma 1 and sigma 2 and sigma 3 become, sigma 1 becomes S yield, sigma 2 is 0, and sigma 3 is 0. So if we go back to this equation, substitute for sigma 1 equals sigma yield, sigma 2 equals 0, and so forth, and then we find that critical value. So having done that, we find that the critical value is given by the following. So we're going to write it down here. U distortion star, because this is critical, is now equal to 1 plus nu over 3e times S yield square. And that is by just direct substitution with these conditions in the previous equation. And we say that when the UD is equal to UD star, then we get failure. This is the yield condition that we have. And when we plug back in everything, we find that we can define that yield condition in very simple equation. And this simple equation is going to look like this. So yield condition is that, let's define sigma prime as equal to 1 over the square root of 2, or maybe let me call it sigma. Instead of sigma prime, we're going to call it sigma sub VON. This is von Mises stress, it's a very famous stress. And it is equal to sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared. And then all of this, you take the square root. So if you define, so I'm going to put 3 lines here because it's defined, von Mises stress in this fashion, then the yield condition based on the distortion energy criterion or theory is sigma von is greater than or equal to S yield. This is our yield surface. So all what we have to do now is find sigma von Mises. What is the von Mises stress, which is kind of a representative, or people call it an equivalent stress. Once we find the equivalent stress, then we compare that equivalent stress to the yield strength of the material, and that tells us whether we have exceeded yield or the design is essentially safe. So I'm going to write a couple of forms for the von Mises stress that are useful sometimes in special conditions that will be helpful in solving problems. The equation that I wrote before, which is, you can see right here, is very general. So this equation here, assuming that we have 3 principal stresses. But in many cases, we don't have 3 principal stresses. We have only 2, or we may not even have principal stresses, but we have other components of the stress tensor. So we may need, in design applications, if we know all of the principal stresses, then fine, we can use von Mises stress by this equation compared to the yield. If we know that we have plane stress, for example, then the third sigma 3 is 0, then we will have, it's a special case, right? But what happens if you do not have the principal stresses? You have the whole stress tensor. What do you do? Well, there's 2 options in this case. Option 1 is to make stress transformations like Mohr circle, and then eliminate shear and find sigma 1 and sigma 2, or in some cases sigma 1 and 2 and 3. Option 2 is not to really do that and use the algebra that we used before, but write it in terms of the components of the stress tensor directly. So I'm going to write these two options here because they'll be useful in design applications. So let's consider here option 1 for the von Mises stress in plane stress condition. Let's say plane stress. This is kind of more common. Then sigma von is going to be equal to, let's say in this case we have 3 stress components, so it will be the square root of actually 2 stress components. It will be sigma 1 squared plus sigma 2 squared minus sigma 1 sigma 2. So it's very easy to write that when we have plane stress. This is in plane stress. In 3D, then we defined already von Mises, and we can use it from the previous equation. Now, option two is when we have the whole stress tensor. So we can do that either in 2D or in 3D. So in 2D, the von Mises stress, I'm going to write it here as sigma x squared plus sigma y squared minus sigma x sigma y, just like before, but we have to add 3 times tau xy squared and take the square root. So this is the red expression is the same as the blue expression in 2D, but we have not done the transformations to find the principal stresses. We just used the stress tensor as is without any transformations. In 3D, then the corresponding von Mises stress is the x squared, y squared, z squared, and then you have now to add the, well, actually without expanding, so let's just do it a little bit without the expansion in here. So we can do it like this: sigma x minus y squared, and then y minus z squared, and then z minus x squared. And in addition to that, I have 6 times now all of the shear stresses, x, y squared, and so on. So I will have 6 times the sum of the 3 shear components here, and so I'm running out of space here, and all of that we take the 1/2 square root, and then from the outside we have 1 over the square root of 2. So these are the 2 options that we have to consider when we calculate the von Mises stress, and I'm going to illustrate a plane stress case where we can actually plot the yield surface next. So let's take a plane stress case. In this plane stress case, we have on the plane that has sigma 1, sigma 2, the yield surface is actually a yield line or yield line, and the line is given by this equation: sigma 1 squared plus sigma 2 squared minus sigma 1 sigma 2 is equal to S sub yield square. So this is the same relationship that define the von Mises stress. On the left hand side is the square of the von Mises stress. On the right hand side is the yield stress square. So once we have this equation, if you look at this equation carefully, you see this is an equation that defines, in fact, it defines an ellipse. So if you plot now this equation on a line, on a surface that has sigma 1 on the horizontal and sigma 2 on the vertical, then that's the equation of an ellipse. We know that the circle, if it were a circle, there would be sigma 1 squared plus sigma 2 squared equals constant, right? This is the equation of circle. But it's not a circle because you have this term here, as we've learned a long time ago. So we have now the equation of an ellipse. And the ellipse, in fact, is not at with the major axis at the horizontal, but the major axis making a 45-degree line, and it looks like this. So you have an ellipse that looks like here, and the ellipse defines this equation. So this is the von Mises ellipse that we've been talking about. So I wanted just to show you now how it looks in for experimentally how this looks like. So if you look at some of the experimental data and you plot sigma 1 over the yield stress and sigma 2 over the yield stress as a normalizing factor, then you have 1 here and 1 here, and -1 and -1, and you have two lines. You have the ellipse, which is the distortion energy theory, and you have another line that the dotted line shows the maximum shear theory. And the data, experimental data that we have is somewhere closer to the von Mises or the distortion energy theory than the maximum shear. However, the maximum shear is, as you can see, is more conservative because it lies inside, and therefore we can use it in design. So the predictions that we will see here is that we get the maximum. We have two lines. You have this is the distortion energy, DE is distortion energy line, and this line here is MSS, the maximum shear stress line. And if we have, for example, pure shear loading, one is equivalent to one stress positive, one stress negative of exactly the same magnitude but negative. That's pure shear. The pure shear loading is going to intersect the maximum shear stress at 0.5 S yield equals sigma 1 or sigma A equals sigma B. And then it will intersect the distortion energy line at not exactly 0.5 but at 0.577. So we can show that just by solving the equation of straight line with the equation of the ellipse. So these are kind of observations that we can show. This is the what we've shown about the intersection at 0.5 of the yield strength, and the intersection with the other criterion, which is the distortion energy, gives you the intersection of 0.577, and therefore it's a little bit less conservative than the maximum shear stress criterion. So let me see if I can find an example here that we will apply before we end this lecture. So I'd like to pull an example in which we're going to compute all of the criteria and compare them to one another. So here's an example that can show us this, and the example is in here. So we have hot rolled steel, and it has yield strength of tension is the same as compression. YC is yield compression, YT is yield tension. 100 kpsi is 1 kpsi is 1,000 psi, pounds per square inch. and the strain at fracture is 0.55, like 55%. So obviously, if it fractures at 55%, then we can consider this material is actually a ductile material, because a brittle material fractures or fails at strains of less than a few percent. Let's say 5%. If it fails less than 5%, then it's brittle. So we're going to apply the two criteria we learned for ductile materials, that is the maximum shear stress criterion and also the distortion energy criterion. And we're given 5 different cases. A is sigma x is 70, y is 70, tau xy is 0. So right away, these are principles because I don't have shear. Case B, I have sigma x 60, y is 40, tau xy is minus 15. Then I'm gonna decide, do I want to use the formula for von Mises directly, or do I want to do stress transformations using Mohr circle? C is a similar idea, but one of the stresses is 0. And D, we have also 2 stresses are negative, and we have shear. And then finally, E has only principal stresses, so it doesn't have, but they're all equal. So let's just do the solutions one by one. And the solutions one by one is we consider each case separately. So in each case, we find sigma prime. They call it sigma prime, but I call it sigma von because I'm not sure if we think of prime as derivative. It's not derivative, it's just a symbol that they use in the book to indicate the von Mises stress. That's all. So we have a von Mises stress for the first case. We have only principal stresses because sigma A is the same as sigma 1 is 70 and B is 70 and sigma 3 is 0, so it's a biaxial stress state. So we have sigma 1 square plus sigma 2 square minus sigma 1 sigma 2, and we take the square root. That's the formula. Apply it here, you get von Mises stress is 70 again. And the factor of safety is the yield strength of the material divided by the actual stress, equivalent stress, and therefore we have a factor of safety 1.43. That's a good margin of safety. Now we go to the maximum shear stress theory. Here tau maximum is sigma 1 minus sigma 3 over 2. Sigma 1 is 70, sigma 3 is 0. Then the maximum shear, which is the radius of the Mohr circle, if you will, is 35. And we compare this to half of the yield, because at yield, the shear is only the shear value at yield is half of the yield strength of the material in tension. So we get the same safety factor as before, no change. Now we go to case B. Case B, we decided to do all of the labor of Mohr circle, which means that I get sigma 1 and sigma A and sigma B. This is the center of the Mohr circle. This is the radius of the Mohr circle, as we learned. And then we can center plus or minus radius give us the 2 principal stresses. And then we use them in the same formula as before, and we calculate the safety factor, taking the yield strength divided by von Mises. It comes to be 1.7. Now we know we can compare to the maximum shear stress, where the maximum shear stress is the difference between the maximum principal stress and its minimum, and that is 68 minus 0 divided by 2 gives us 34, and therefore we get a factor of safety of only 1.47. So in this case, the von Mises yield criterion gave us a higher factor of safety than the case of maximum shear stress. So it just illustrates that you have, when you consider When shear is in play, then the results can be dependent on which criterion you apply. So moving on to the next example is C. And C, we do not do the Mohr circle transformation. We go directly to x squared, x minus y, xy, y squared, and then we add the 3 times tau xy squared. And therefore, that's a pretty fast way to compute the von Mises stress of the material and compare it to the yield point, give us a factor of safety of 1.14. Now, when we come to maximum shear stress, then we also have to use the Mohr circle equation for the radius of the Mohr circle, given that we have sigma x, sigma y, and tau xy. And that gives us a factor of safety of 1.02. Case C, we have negative principal stresses here, but it doesn't matter, and a shear. So we get the 2 principal stresses that turn out to be negative. We use the same formula, so it turns out to be that von Mises stress is positive, and it gives us yield stress factor of safety 1.7. And compared to maximum shear, then we see that we again more conservative when we consider the maximum shear stress theory. So the idea behind this exercise here in D is that although you have compressive stresses everywhere, negative, but the von Mises is always positive. Okay, so it's something that we have to think about. What's the meaning of von Mises? The meaning is that it's a positive, is like an energy, but it's kind of in the form of a stress. So you have to think about it as a distortion energy, but is expressed as a stress. So it's always positive. Whenever you find like finite element results expressed in von Mises, it's always positive from 0 to whatever value. Whether you have compression or tension, it doesn't. It's kind of agnostic. It doesn't know the difference between compression and tension. So now the last example here is E, and in E it's kind of unique because we have a hydrostatic stressed state. All of the 3 principal stresses are equal, and there's no shear. Then when you compute the von Mises stress, it turns out to be 0, which is what we expect, because there's no deviation, there's no deviatoric component, there's no energy stored in the deviation from hydrostatic stress state. And in this case, the factor of safety is infinite, meaning that it is absolutely safe, and the same thing for the maximum shear strength stress theory. It gives us the same result for the factor of safety. So in summary, we just have to be cognizant of the forms of the stress that comes to us and use appropriately just for speed. Or if we are short on time, we can just use directly the equations that we described with the full stress tensor without doing a Mohr circle transformation or a stress transformation. And with that, we are going to stop the lecture, and we'll see you next time when we continue to look at other possibilities for failure when we have differences between failure in tension and failure in compression. Things become very interesting because, as we see in brittle materials, for example, they can take a lot of load in compression, but they will take very little load in tension, and therefore concrete, we cannot treat tension the same as compression. So we'll wait until next lecture.